Today on Flight 9 of the Hakan Modified Lancair, introducing Hakan's stall vane and a hydraulic problem.
Worth noting, I think I'm sitting in a puddle of hydraulic fluid right now.
Oh shit.
Hi, my name is Elliot Sigwin and this is a flight test video for the Hakan Modified Lancair. The airplane was modified by aerospace engineer Håkan Langbro. This is Flight 9 of the aircraft. If you want to see the preceding flights, please go ahead.
1, 2, 3, 4, 5, 6, 7, 8, 9.
Before we get too carried away, I want to make sure we thank our sponsors. First off, I want to thank the Patreon supporters. I can't believe the support that's come in recently via Patreon. We all know how hard the world is right now and it means a lot. Thank you. Also, I want to thank Method 7. Method 7 makes a fantastic set of eyeglasses for the aviator. But even more so, they're active in the community and have supported Wasabi for a long time, and we really appreciate that. Lastly, I want to thank Butler Parachute. I've been wearing a Butler Parachute for as long as I've been flight testing airplanes. It's absolutely critical for the work that I do to be confident that I have an alternate escape plan, and Butler gives me that confidence. Now, let's get back to the show. So, plan for today. I'm going to put wingtip and tail looking at this left wing, or right wing.
Yep.
And then it's all focused on this wingard area, right?
Correct. And here's the thingy.
So the thingy is the magical part of this whole test flight.
So I think I will be able to see it.
Sorry, do that again.
Yeah. So when it starts separating, right? When it starts working, it's going to go up here, I think. So it's going to hit all these tufts.
Okay, so we don't need more tufts.
No, I don't think so. I think it's going to be good.
Do you have a name for that?
Call it the vane.
When he's motioning with his hand, that's where the vortex would lay, right in the wing body fillet. We're taking high energy air and mixing it with the energy that's stalling out or losing energy right at the surface and trying to keep that boundary layer attached. I couldn't find anything that said what Cirrus called it.
I saw a few articles and I don't know.
There was a lot of like great press around it, you know, them being excited. Cirrus calls it a fuselage vortex generator.
Yeah, I don't know. I would call it the stall vane.
So how did you set the incidence on it? Obviously that's critical.
Right, so I did the CFD, cruise conditions, so I got all the streamlines, the oil flow, figured out where that was, measured it, and designed it and put it in there, ran it in the CFD, and it lined up with the streamlines within 0.2 degrees, something like that for cruise. Cruise, I used 0 degree AOA.
So the question he was answering there was how he picked the incidence of the part in CFD. You can see him talking about how he located it in CFD, and then he's checking with the aircraft at a given AOA what the local flow is doing, you know, because it has to go around the wing, etc. My question was about once he had the answer where he wanted it to be, how did he install it on the airplane? Okay, so CFD told you what angle to put it at.
Yes.
How did you know how to put it at that angle on the airplane? So that moment was interesting for two reasons. The first is that being an engineer, my question, which was a practical application question of how did you install it? He's an engineer used to talking about analysis, so he answered the question talking about how he did the analysis. The second reason is interesting. I think CFD has a lot of voodoo around it. People assume that if you have a good CFD model, you've got everything. And what we just pointed out was that assuming his model is correct, there's still the question mark of what is the AOA for a given condition, right? So if you think your AOA is 6 and it turns out to be 5.5, in the case of the stall vane, it doesn't matter. But in the case of some other stuff, it may matter. And so there's the joke with any computer-based analytical tool is that it will always give you a pretty picture. CFD is no different. It'll always give you a pretty picture. But whether or not you can believe it is a separate thing. And I think that that's some of the most interesting work in flight tests and why this project gets me so excited is because we have both the practical side where we're making stuff and sticking it to airplanes, but on the other side we have to go back to actual analytical tools and figure out what we wanted to happen.
From the leading edge, where is that point, for instance? Right?
Okay, as far as forward of the leading edge.
And also found this point here where the fillet starts, for instance.
Okay.
And I measured it vertically to come up with whatever the vertical point is here.
Yeah.
And then I did the same thing, and then I measured the angle here, which is always 0.
Oh, sure. So that's a good reference.
Then I put my leveler on this one, rotated that one to the same degree, and then made pilot holes, clecoed it in place, and then drilled it and so forth. Did the same thing on the other side.
And it's installed right now with pop rivets?
No.
Oh, wow, cool. Cool.
Bolted. And then, yes, and then I did the CFD with, I think it was 13 and 14 degrees AOA to see where it ended up. You know, nice vortex lined up all over the fillet and cleaned up the area back there.
So here's some screenshots of the analysis that Håkan's talking about. You can actually see the vortex in CFD laying right there in the wing body fillet.
And then my other CFD friend did the same thing with certain AOAs and whatnot, different software, all that kind of stuff. But he verified that the same thing that I come up with. So now it's just the proof is in the pudding, right? So we'll see if it actually works.
Okay, so and then global picture. So the you wanted to shed a vortex that's going to clean up or reattach that area there at the wing root?
Yes.
Doing the same work that was previously done with those big VGs we had there for flight 7 and 8.
The big VGs we had before, they were located here.
Those VGs are extensively covered in the videos for flights 7 and 8. Feel free to go back and check those.
Right before the
Yep.
things here.
Yep.
And I also had 4 of them back here. Those we removed, and these are removed. So hopefully it will do the same thing. It's all about keeping this area here attached, but you know, with the vorticity, just to keep the boundary layer, you know, lined up here. So we move the stall outboard.
So there's the VGs that we're talking about on flight 7 and 8. Those were actually made out of a piece of L extrusion that Håkan found at Home Depot and then hand cut out himself. Just used double-sided sticky tape to stick them on. But again, that's all covered in flight 7 and 8. And you said your friend did some of the CFD. What's his name and how do you know him?
His name is Leonard Wish. I worked together with him at Piper. Known him for over 20 years. And he volunteered to do that too, and so far that looks really good. And so we'll see. Keep fingers crossed. And yeah, because the other good things with that one is that it doesn't create any drag in cruise, right, since it's lined up with the streamlines and all that kind of stuff. And he estimated it was like 1 or 2 drag counts of drag, which was like less than 1% of total drag for the aircraft, which is basically negligible, you know. So if that works, so much better than the VGs, because they will create cruise regardless,
right,
or create drag.
They're doing the same thing regardless of angle attack.
Exactly.
Okay, before we move on from that topic, let's just do a quick recap on how the fuselage vortex generator or the stall vane works. So fundamentally, it's very similar to a vortex generator, right? Where the idea is we're just trying to mix the air, right? So that boundary layer air, as it goes across the top of the wing and moves further and further back, it starts to lose energy, right? And as it loses energy, it gets more and more likely that it'll tumble. When it tumbles, that separation is what begins the process of creating a stall. So a vortex generator is just like a little finger that reaches up and grabs, reaches up through the low energy area right above the surface, that low energy boundary layer, and up into the high energy area above, and grabs it in, brings it down, and mixes it with the low energy air right on the surface. The problem with the vortex generator is that these little blades that are, if we're going this way, these little blades that are mounted in the free stream, is that no matter how fast you're going, they're always there creating turbulence. They're always there doing that mixing, and that mixing takes energy, and that energy is drag that slows the airplane down in the cruise phase. The difference with the stall vane or the fuselage vortex generator is that while at high angles of attack, it has that angle of incidence that creates the vortex and protects the wing downstream. In cruise, it's fared into the free stream, right? Which means the only drag is just the surface friction of a very small, this big piece of material sitting in the breeze, and that's the advantage.
And the other thing I did, I removed half of the VGs for the aileron, also to reduce the overall drag, right? So before it was one this way, one that way.
Oh, got it. Okay.
So I removed the first one of the pair for each one of them, and I took the inboard one that was here, put it out here.
Okay, cool.
And the reason for that is that when the flaps are down, your flow goes more locked in. It gets sucked into the low pressure area of the flaps, right?
Okay.
So that one really wasn't needed because that one already
it's being sucked away
there.
inboard, yeah.
Yeah. So put it here, so we're gonna get a little bit better control.
So here are some screenshots of that CFD showing where the vortexes from those VGs in front of the aileron end up. And just like Håkan's talking about, you can see they get sucked way inboard by the low pressure from the flap, and explains what he's talking about. Looking at the video from 8, I finished the video last night. I had the stalls. I didn't quite get them out, but there's a lot more lateral directional stuff on 8 than 7.
Okay.
So I think remember the big thing was I don't know anything, but it seemed like the biggest thing would have been we pulled those last, was it 4?
Yeah.
And I didn't think they would have as much effect as they did. Now it could obviously just be something different I was doing, but there was way more wing drop at.
Really? Well, we can always add more. You know.
This is the thing, right?
Yeah.
This is what makes it cool.
I think it went all the way up till here somewhere.
I believe so. Yeah.
2 more pairs if you count the pairs, right? And I don't mind adding a few more out there because that's minor drag, and if it really helps the lateral control, then definitely we can do that. Definitely.
It's just it's always a trade-off between what's acceptable lateral handling in the stall and how fast you want to go, right?
Exactly. Yeah.
Right on.
And then let's see, engine-wise, I replaced the intake gaskets for 2, 3, and 4. Leveled as much as I could for the receptacles and the tubes, and clean up the interface and all kind of stuff, put them in. So hopefully the engine will run a little bit better.
Okay.
Because you mentioned it was running rough and EGTs were a little bit scattered or whatever.
So it goes without saying that the engine performance stuff is important because we did all this stuff to improve the stalls and the airplane slowed down, and now we're trying to prove or make the airplane go faster. And so if there's missing horsepower, that would explain the problems we're having with cruise speed.
And the other thing I looked at was the carb heat valve. So when I looked at that, it was kind of stucky, and it really didn't open and close properly. So I don't know, it really has any influence to it, but one thing could happen is that you get too rich of a mixture and it might mess up the engine something. It might also lose some manifold pressure. I'm not so sure about that, but it might be a possibility. So I fixed that, took the whole thing out, cleaned it, straightened the little wire and bolted it up and made sure that it hits the end points and closes properly. And the other thing I did, if you look at this, I removed the center throttle from the console.
That's a lot of work.
It wasn't too bad actually. What I did, I put in a new push-pull.
Yep.
That one, and I connected them now, so now both works.
Okay.
So, and they hit the stops, and we talked about high idle before. So first time I ran it, it ran good, and then second time I ran it, it was like 960, and I thought it was too much because I taxied to the fuel pit, and I had to go on the brakes all the time. So didn't want to do that. So cowling off again, adjusted the idle. Cold, it was running at 600, something like that. So I expected at warm, probably about 750, 800. So that should be good. So that's probably good. And then the little bar that I had in the nose gear well to hold the cables in place, I removed that one. So hopefully now we won't have any problems when the nose gear goes in and hitting any of the engine controls. Probably wouldn't see any movement there, which
So if there was a loss in manifold pressure during the cruise points on the last flight,
hopefully
it was from that bar, and that should be fixed.
Yes. And if we can't get the manifold pressure that we expect, then we need to figure out why that is, because the numbers we had last time, was it 19.5 at 8,900 density altitude? That's way too low. It should be up in the, I would say, 22 range.
At 22 is atmospheric pressure, so.
Yeah, exactly.
So you expect more.
So we'll see what goes on with that, but that would explain why we didn't see the speeds that we expected, because that's more like, what, 55% power or something like that, right? So we'll figure that out. Then I also replaced the
charging cable.
Yes, I had to try out 3 of them.
Really?
Yes, and then I had to Google, and I had to go talk to the avionics guys and ask about the problem, and it's an obvious problem because many people have it, right? So you have to buy the higher end units
The cables.
Yeah, no, not the cables. The little cigarette adapter
Oh.
itself.
Huh.
Because the lower end, they're not built properly and whatever, they cost static. So I got one that was recommended, put that in, and so now we don't have any problem with that.
Cool.
And I also replaced the cable that was a little bit frayed
Yep.
last time, so that's a new cable. So yeah, that's pretty much it there. So hopefully we have, taken care of the known issues that we had last time, and then we'll just try it out again.
Cool. Go ahead.
This one here. So you can see the blue streak from the gas, right?
Sure, yeah.
So what I think happened was that the valve, the interface leaked and it got sucked in here, where the split is for the wings, and then drawn up to the top side. And that was always the big issue. Why is it leaking on the top side, or is weeping on the top side? I couldn't figure it out. And started looking at it because there was no apparent leak from the tank. And it was not a leak, it was just, a weep of some sort. So what I think happened was that the drain valve leaked between the valve and the wing, and then it just slowly seeped and came up on the surface. So I drained the tanks, pulled it out, cleaned it up, and did whatever stuff to clean that. And it is a tapered thread by the way, but still that obviously didn't help. So I put an O-ring in there and some thread sealant, fuel safe thread sealant. Cleaned it, put it up, filled the tanks, and that was, I would say, 3, 4, 5 days ago, and it's still dry. So
That's a huge difference.
yes. So I'm hoping that was the issue, because I really don't want to take the wing off again. So I have all the material, all the cores, all the parts for the new trim tab.
Oh, cool.
Yes. So we're going to start working on that maybe tonight or tomorrow. So I just outlined the size of it.
Oh, cool.
It's going to be this big. I want to make it big enough, because if it's big, I don't need a lot of deflection of the tab, right?
Oh, sure,
I'm not going to stall the tab and whatever, So yeah, so obviously I have to go in and cut this out, clean it up. Had to build a little new web on the inside here, and and then build the tab itself. So got the core cut by the company up in San Francisco. Got that. Had the design laid out. Already cut had the kits for the carbon fiber done, and so it's just a matter of get going with that.
What's the company in San Francisco?
Foam links.
Foam links.
Yeah.
And they do hot wiring, CNC hot wiring?
They do hot wire, CNC, 3-axis, 5-axis. They work for the, any type of industry that needs some foam. They also cut the molds for the fillet.
Okay.
Yeah.
Cool.
With the CNC stuff.
And good pricing and all that?
They're reasonable. Yeah.
Cool.
So, yeah. Well, so I've been talking to Dynon and all that kind of stuff, and trying to figure out how to do the new panel. And obviously it's going to be, going to take all that thing out. But it's going to be two 10-inch displays, and then I'm still going to have the iPad as a backup, and then I'm going to have the Garmin GNS 355 as my GPS WAS for IFR approaches and stuff like that. We're going to keep the audio panel. We're going to keep the ICOM 220 radio.
Okay.
And then I'm going to make a new center console kind of thing, probably carbon fiber.
Cool.
And the panel is going to be angled in such a way that it's more or less always facing the pilot.
Cool.
So it's staggered a little bit like that. And then probably going to have the VPX Pro electronic circuit breakers.
Cool.
Make it clean.
Yeah.
So I did all that stuff in CAD, laid it out, measured the cockpit and everything, so I know everything works. And yeah, so it's time to start ordering parts.
Oh boy, watch out. With all the discussion about angle of incidence of the stall vanes, Håkan and I decided to go ahead and put some more tufts on the right stall vane, which is visible from the camera, so we could get some idea of not only its incidence at stall, so we could see whether or not it was generating the vortex there at the vane as expected, but also in cruise, we could see if there was any incidence, and therefore if we were at the lowest drag configuration. Let's write down what we already talked about.
Yeah.
All right, so it's a normal takeoff. We're going right to stalls, so we're going to climb right to 10.5. So again, in the interest of giving you guys everything we got, on a much bigger, more formal program, the test card would have been generated before I arrived for the day. So in these little programs, we're trying to minimize the amount of burden on the program, so we try to not be on the charge number as much as possible. So while Håkan's typically sending me updates, in the time that I'm not there on what he's doing to the airplane, so I know what's going on, there's always to make sure that I'm really focused on what's going on. The maintenance brief is a critical part of that interaction, right? Where it's just sort of both of us talking through and making sure that we're both thinking about all the things that may have changed and then how that affects the flying for the day. In this case, we're kind of wrapping everything up, right? We're bringing all the strings together that are the program, driving towards a minimum approach speed demonstration, and then finally a Hakan checkout. So just trying to make sure we're getting the most efficiency out of each one of these flights, and there's a lot of loose ends that we're trying to kind of tie up here. Climb power. Do you want to bother with the alternate static anymore?
No.
I had this nightmare. I woke up the other night like, what if I didn't change the alternate static on all those stalls? So I went through on flight 8 and looked at where the alternate static was on every flight. It was right where we're supposed to be. Like it was like it woke me up in the middle of the night. Like, fuck! What if all that data? I throw it out? God damn it! And then so it'll be at least 3 stalls. Your landing configuration. Do you want to do 35 and 45?
Yeah.
So then we're going to do you want so minimum speed Clovers flown 35 and 45 or just 45? Likewise, because there's some open-ended items out there still hanging, like we talked about in the previous videos, there's still a question about whether we're going to be using 35 or 45 degree flaps in operationally. And so the question is, should we be doubling all the work at this point, or should we just sort of pick one for now, right? As we until we get settled.
So the stall speed is just a few knots in between 35 and 45. So I think pick one.
And I think 45 is the most likely going to be your landing configuration. So for climb rate check, that'll be at wide open throttle, full forward on the blue knob. And then you want to just use 125 knots, which is the climb speed clean. As we get ready to make this big step of demonstrating landings with the flaps deployed, a really critical thing is just dealing with safety, right? And a lot of that safety is the aborted landing or the climb away. Somebody pulls out on the runway or whatever. Ramona's a busy airport, so we wanted to do a climb rate check in landing configuration. Counterpoint being that 737 on a go around doesn't leave the flaps all the way down. Flaps to take off, then positive rate, gear up, and then flaps retracted. But we wanted to make sure we had some idea of what that profile might look like and how much available excess power was there in the event that we didn't get to the flaps on this high risk landing in a new configuration scenario.
And land, push forward. What speed are you at?
So you fly the approach. If you're flying it at 1.3 and stall speed's 50, that's 65.
You probably would never do that. You probably would fly a little faster. It depends. So it all comes down to how the aircraft reacts. But I would say if you go around, you should do that at 75, 80.
That's where I was at.
Yeah.
So pick one.
Let's do 80.
80.
At least it would give us an indication. The aspect ratio of this wing is way higher than the RV, so it's probably not that of a rock kind of thing.
So 75?
No.
So in this hypothetical scenario, we're approaching at 1.3, so assuming stall speed's 50, we're at 65 knots coming down in. Someone pulls out the runway, tower calls a go-around. We're going to stand the power up and not retract the flaps, which is our conservative scenario, accelerate to 75 knots, and then climb at 75 knots. And the question is, what is our climb rate in that configuration? After looking at the climb rate, we'll make the decision what the landing configuration will be.
Yeah.
So I will make that decision now.
Mm-hmm.
Okay, so I got 2 Cloverleafs, one in landing configuration and one in cruise. Sorry, 2 each.
Yep.
And we'll talk about landing configuration. Do the brief once I get my PJs on. Cool. So brief mission overview. So we're going to take off, climb to 10,000 feet. We're going to check stall speed and the landing configuration, both 45 and 35 degree flaps. Then we're going to check climb rate with 45 degree flaps and gear down, then 45 degree flaps and gear up. Then we're going to do a Cloverleaf low speed, so that'll be +5 on whatever we determine the 45 degree stall speed is. And then we'll do a Cloverleaf in cruise. So wide open throttle, 2,500 RPM and 8,000 foot pressure altitude. We're going to do 2 laps on both of those, using the iPad for GPS.
Right.
And then we'll discuss the landing configuration before we do the landing. Depending on what the climb rate looks like, we may try flaps down landing for this flight. Fuel, we're full.
Yep.
And we'll plan to do, before the Cloverleafs, I'll switch tanks. So take off on one, land on the other.
Do you use the primer solenoid thing when you start, or do you just pump?
You mean pump the throttle?
Yeah, you can use the primer thing if you want to. I tried that the other time. Initially, I thought it was an issue with the spark plugs and all that kind of stuff, but I don't think that's the issue. So if you want to just pump on the solenoid for 1 or 2 seconds.
So the pump pressurizes the rail, and the solenoid opens a valve that goes to the pressure. And yeah, we had said not to use that initially.
Yeah,
okay.
Use it if you want to.
So I think what I've been doing is pump on and then just stroke the throttle like you would with any carburetor.
Yeah.
If you want to try that, yeah, okay.
Either way.
So we'll pull out, start up here. No issues there, nothing strange. You'll be at the picnic table. Taxi out. There's no weird takeoff stuff. You want to make sure we take note of takeoff manifold pressure. Plan to climb at climb power, which is 2,500 RPM and wide open throttle, 125 knots, 10.5. Work areas will be the same to the north. There was one spot when I got pretty far to the east, it seemed like you were having trouble picking me up. But in general, the radio stuff last flight wasn't that good. With 2 radios, maybe we'll see if we can figure out what's going on there.
Right.
So the question is, what altitude to do the climb rate stuff at, because of the limited power?
5K maybe?
The only thought is, like, because we're 10.5 for the stalls, and then these Cloverleafs here will be at 8. So if we do all this at 8, that's kind of. I guess if we descend down to 6 or something on the stalls, then because I wouldn't go below 6 on the stalls. But with I don't know if I can get all 6 stalls done before 6,000 feet. So it's probably 2 climbs. Is there a minimum altitude for the climb rate check? I mean, pattern altitude, right? I mean,
Well, that would be pattern, but we can't do it.
right. I mean, it's a joke. There really isn't, from a safety standpoint. I'm not worried about departing the airplane. I guess the risk would be a flap getting jammed, but I think we've sort of taken that off the table at this point. So there is no minimum altitude.
You just need to get an indication.
Is there a minimum altitude for the low speed Cloverleaf? So you want to shoot for 6 on all that?
Yeah, we can do that.
With the stall vanes, there's a risk of a lot more lateral directional stability stuff in the stalls. So I'm going to just do a real good job keeping the ball centered to try to get the most representative stalls.
Right.
We're going to slow the decel rate down a little bit.
The primary thing is to see if there's any major difference between the original VGs and the stalled vane and what that might be.
And that's a flow thing first. First is the way the tufts look.
Yes.
Second is a
stalled behavior.
like a min speed. Is that even on the because we don't have an airspeed indicator. But stall behavior handling qualities would be probably 3rd because it's so qualitative.
True.
And we're going to check the climb rate and talk about that as far as how we're going to fly the approach. And then for the Cloverleaf, I'm just going to use whatever we decide the stall speed is, which is going to be right at the bottom of the gauge,
Yeah.
plus 5.
Right.
So it's probably going to be 55-ish, and see if it's stable there. If it is, we'll do it. If not, maybe we can go faster. If it's real stable, maybe we can go slower.
Yeah.
Of course, there's a question if we don't have enough power to hold altitude.
Are you going to use the chute?
I was planning this is probably the last flight with the parachute.
Flaps are coming out.
Okay.
Okay, full flaps are set. Retrimming. Okay, here comes stall number 1, 80 knots. 5, 70, 65, 60, 55. Oh, that was cool. So I was able to hit the aft stop. There was no noticeable elevator stall, but there was definitely a change in responsiveness for the last 20% or so, right about the time we get to minimum airspeed. Nice slow wing waggle, but nothing dramatic.
You'll notice that above my left shoulder there was not a panel-looking camera. I ended up reshooting these points after I did the 35-degree stalls.
Here comes number 2. 80 knots. 75. 70. 65. 60. 55. Call mid speed 50. So that's 2, that's 8,500. Here comes number 3. 75. 70. 65. 60. 55. Just slightly below 50 on that one. That's 3 in that configuration. I'm going to power up and climb back up.
I called that stall speed 48 knots.
Manifold pressure.
17.7.
So would you say that it feels slightly different and the other VGs had better control?
I'd say force in the pitch axis has gone down from when we had the VGs on there, but it's nowhere near as light as the first couple stalls that we did on this program.
Okay.
The lateral directional stuff was very nice, very benign.
Okay.
I would say it's absolutely comparable to the VGs, with just that slight difference in pitch force, but nothing serious.
All right. Thanks.
Yeah, that's super cool. It's a lot simpler device than having all those VGs all over the place with very similar results.
Definitely. So the only thing that worries me a little bit is the lighter stick force, but if it's nothing, significant, then they're on the right track.
So, initially, before we put the VGs on, there was a step change in elevator force right about the time you reached sort of peak AOA.
Right.
In this case, it was much more of a ramp of drop-off in force. So that big cliff wasn't there. It just felt like there was less force than we had seen previously.
Okay.
Okay, starting to reconfigure now. Okay, 35 flaps are set. Power's at idle. Okay, here comes number 1. 80. 75. 70. 65. 60. 55.
Lancair?
Maybe just a touch over 50 on that one. Just the slightest right wing drop. Here comes number 2. 80. 75. 70. 65. 60. 55. Call it, maybe just a touch over 50 again.
All right.
And here's the last one at 35. 80, 75, 70, 65, 60, 55, and recovered.
I call that stall speed 50 knots.
I'm going to do a couple more at 45. Here come the rest of the flaps.
Yeah, sure not. Why not?
So this is the reshoot after I installed the camera as I was supposed to.
8,000 feet. $80, 75, 70, 65, 60, 55. Just a touch under 50 on that.
All right.
Do 7,500. Let's get this last one done. 80, 75, 70, 65, 60, 55. Okay.
And I estimate these stalls at 48 knots.
And up next we have a climb rate check with 45-degree flaps at 80 knots. 6,000, descending to 6,000.
All right.
Full RPM is set. Mixtures as a reasonable medium setting.
Okay.
80 knots is set, and here comes 6,000. Power's coming up. Full power is just over 20 inches, 20.5. And we are climbing.
In this configuration, I timed a climb of 500 feet. I estimate the climb rate for that climb in that configuration of 275 feet per minute.
And that's wide open throttle, full black knob, full blue knob showing 2770.
Okay.
And we're noting we break 75 on these, but I'm doing them at 80.
Okay.
My mistake. Okay, I'm going to hold it right here and just pull the gear up. Gears up.
Similar to the gear down points, with the gear up, I timed a climb from 6,500 up to 7,000 feet, so that's a 500-foot climb, and I estimate the climb rate at 325 feet per minute.
And just about 20 inches, 19.9. 50 feet to go on a 500-foot climb. Okay, there's 7,000. I'm going to pull flaps up.
All right.
Worth noting, I think I'm sitting in a puddle of hydraulic fluid right now.
You're out of hydraulic fluid?
I'm sitting in a puddle of it.
Oh shit.
Is it a big one?
I can only see like a tablespoon, but I can't see directly under my butt.
Gotcha.
And it looks like it's in the right seat well as well. Did you do any work on the hydraulic system?
None whatsoever.
So when I pulled up the gear after doing the stalls is when I started to notice sort of a warm feeling in my butt area. I didn't really think much of it, but as time wore on, I started to wonder about it more and more. And that's when I noticed over in the right seat, where the right seat would be, a puddle was starting to form of hydraulic fluid. So in order to make me fit in the airplane, we had to take all the cushions out. In order to make the parachute fit, we had to take the seats out and the seat back out. So I'm sitting basically on the bottom skin of the wing. And as a result, all the hydraulic plumbing for the inner gear doors is right there in my seat, as well as all the control stuff, etc. With the inner gear door lines right there, when the inner gear door actuators failed, with just a leak around the shaft seal, it was just injecting hot hydraulic fluid into my flight suit.
Looks like it's the gear door actuator in the right seat that's leaking. Or it could be the line itself. So we got 2 gear cycles left if we do the Cloverleaf. What do you think?
Yeah, go ahead.
Okay, I'm going to set up for the slow speed Cloverleaf.
Roger that.
Just so we're clear, I could see in the right seat that not a lot of fluid had been lost. I was making the assumption that similarly not a lot of fluid had been lost in the left seat where I was sitting. And so I knew that I had 2 more gear cycles left. We had to do the gear down for the slow Cloverleaf, and then we had to do the final gear down to land. So rather than do like an emergency, like get down on the ground, it didn't seem like it was that sort of a situation, especially being so light in the card. The goal was just to get the rest of the data, get down on the ground, and figure out what was actually going on.
Okay, we're configured and decelerating down to 60.
All right.
See how that looks, and we'll try 55.
Yep.
60 works, I'm going to slow for 55. Well, this one takes both hands. Stand by. About 15 inches to hold altitude.
All right.
So the 2 Cloverleafs that I flew worked out to 53 and 56 knots of ground speed, which works out to about 48 knots calibrated. That means that the airspeed indicator is indicating high, because the indicator was showing 55. We were actually at 48 by about 15%. That also means that the air stays constant from 1.1 all the way down to stall speed, and we have a stall speed of 48 knots. We're actually stalling closer to 40. I flew that Cloverleaf again in cruise configuration to confirm the drag reduction, moving from the VGs, the big tall VGs, to the stall Vane. Those cruise Cloverleafs worked out to about 140 knots indicated, but the calibrated speed based on the Cloverleaf was about 134 knots. So again, we're seeing that the airspeed is indicating high instead of the 14% or whatever it was down at stall. It's more like 4% in cruise. So 134 knots is below the goal that Håkan had for the program. But as we talked about, I think we're going to end up just leaving that for Håkan to do on his own, and just focusing on the slow side and safety, getting Håkan transitioned.
I'm going to do a simulated approach at 35 degrees flaps and 85 knots with a go-around. If that goes well, we'll use that for the approach.
All right, sounds good.
So here we did a simulated approach to a go-around. This was a last chance to get comfortable with the flaps down configuration before we attempted the high-risk landing. Landing stuff, anything near the ground is some of the most high-risk testing you can do. But one more simulated approach wasn't going to take very long and could reduce the risk a little bit more. I just flew it at the simulated approach speed at minimum power, just like we were coming on the glide slope, took it into a flare, and then in sort of a worst case scenario, added power to go around and looked at how the airplane responded to the torque and how long it took for it to start climbing, what to do with my hands as I clean the airplane up, etc.
And I'll just leave the gear down rather than cycling it. Okay, flaps 35 set. Simulated final. Simulated flare. Simulated go around. Okay, I'm comfortable with that if you are.
All right, sounds good.
So here we have it, sort of the first or one of the last big milestones of the program, the first landing with flaps deployed. Again, this is not the most aggressive configuration. The idea was to build up to that. So this is 35-degree flaps with an 85-knot approach. Also, we had all of our external cameras had flamed out by this time. In fact, I think one of the cockpit cameras had flamed out. So I don't have really good coverage of this, but nonetheless, it's an important moment for the program. So we're looking at, I don't know if, would you call that a puddle? A little hydraulic residue. There's a matching mark to that one on my butt. And now it's on my hands. But it appears to be coming from the shaft seal here on the inner door actuators. And if we had the seats in, we wouldn't even know it was there.
Exactly.
But since the seats were not in, I could feel the hot hydraulic fluid on my butt. As far as flying, I don't think it's going to get better. So what I was going to suggest for our next flight is just beat the pattern up. Because I don't know if you saw besides just in general bouncing it, I think I was wheelbarrowed like you said.
Oh, yeah.
And so I think that pushed the nose back up, and that's why I jumped back in the air. Oh, yeah. So I was so excited to go around and shave another 5 knots off, start figuring this thing out.
What was the speed you had?
That was 85 approach.
That seemed to be way too much.
It was way too much. It was awesome.
Yeah.
Well, I got down there in the flare and I was like, boy, I'd really like to get like another 2-3 degrees angle attack. I'm like, well.
So how was the ground attitude, visibility? It must have been different, right?
Absolutely. It was way different, and the tail felt high, and that's where it was all I had to not hold it off. But I was, the idea was we had some margin on stall, so I didn't want to sit there.
Tail felt high. What do you mean by that?
The nose felt low.
Yeah, but not stick force-wise.
Oh, no. The forces, all that stuff was just as we felt up high.
Okay.
An unforeseen advantage of the low-speed Cloverleaf was I spent a lot of time, whatever that was, 25 minutes at 1.1, just hanging there, right? And so getting all my, because there's, with the camera mounted there and the DG, it's hard to see the yaw string.
Yep. Mm-hmm.
And, you're busy, and all of a sudden, I feel starting to roll over, and I'm like, oh yeah, and look up and this yarn's way off. And so that gave me a lot of confidence in the pattern I didn't have to be looking at the yarn to know the ball was centered, just because like it's a new place and I don't know what's going to do with the part. So as a result, I felt pretty stable on the whole approach. You know, lateral directional, like we just talked about, but also longitudinally. It all felt really good. I carried power through most of the approach.
Oh, I'm pretty sure you did. Yeah.
It wants to come down with those big flaps on. So, yeah, I don't know if you heard me. I had to add quite a bit of power on the final.
No, I didn't
to get back to the glide slope. I was falling below it. So,
okay.
So that's, you know, that's a new thing with this airplane, right? I'm used to these long, shallow approaches, and so like trying to, like, God, it seems really short, and then wasn't short enough.
So you should be able to do that at 75, 80?
At least, if not slower.
Yeah.
Yeah, and like I said, I was excited to go do that, and then it's like, man, we should probably look at the hydraulic system.
Right.
There you can see the hydraulic fluid stain on the butt of my flight suit. Your comment about not rebuilding the gear door actuators, like so many things, right? Like, well, you know, the big one's the one's doing the work. Well, they're all in the same hydraulic system. It turns out you fail one, you fail them all. So, fucking so easy. You do 1,000 things like that on a big project. So I would say the stall vane as now, as far as stall handling, is adequate.
Okay.
Based on the cruise stuff, it appears it's a little bit less drag than the board VGs, but maybe it's in the noise. So maybe you could make the argument that for cruise you could have it better placed. We can look at the tapes and see that. But as far as the stall side, I think it's closer. You know, it's plenty. So
Slightly lighter stick for
just slightly. And so if you make the assumption the high side of the envelope is going to come up over time as you work on the airplane, and that's beyond the scope of this project, then the next step would be coming up with an appropriate approach speed for the airplane. So we did the landing, and it was a big old bounce, which was partially pilot error, and secondly, I think it was going to wheelbarrow, and so touching down created a bunch of angle attack. Right. So I'd like to do that again. That was an 85 knot approach with 35 flaps. I'd like to move towards, 65 and 45, maybe 45, maybe 65. I don't know, but I think it's sort of 5 knot steps. You sort of beating up the pattern, seeing how it all feels. 75 felt. 85. Felt fast. 85 felt fast. All the way felt fast from the end of the runway. Like the whole time, I kept wanting to bleed it off. I'm like, no, let's do something more representative of an actual flare and touchdown rather than sit there and hang and let it bleed and drop a wing or something. You know, we had the added speed in order to protect us from the stall. Let's use it, not. But yeah, it was definitely tail high on touchdown.
Right.
So if I was going to fly again, it would be beating up the pattern, taking small bites at the approach speed and flap configuration until we see where the airplane kind of wants to be. In order to do that, we don't have to swing the gear. So one could make the argument that we can ignore a leaky hydraulic seal. You're not going to fly with a system not pressurized. So the system will be pressurized the whole flight, so there's pressure on those. No, because it's the doors are open now.
Pressurized down, so
it appears it's the closed side that's leaking.
at 45 or 35.
Well, I mean in general, like, full power climbs on an order of hundreds of feet a minute. So the gear down, it's not going to.
But that was at 6,000 feet.
I mean, even just close. But yeah, I hear what you're saying.
Even so.
But I guess I'm anxious to get more out of the day. I don't want to give up here.
Right. I would say let's do some paddle work out the speeds.
Okay.
See how that feels. Do you need more fuel for that?
It'd be nice to get back to it so we know where the gas is. And I got some battery stuff. Cool. Get it done. Just a little.
Well, it seems to be doing its job. It looks a little funky right where it's at, but everything is just perfectly aligned all the way back.
Wow. That's really impressive.
Yeah.
That you were able to get it. I'm nothing
It's
against
so
you.
close enough, yeah, wow.
Right, so if you were to...
Dip it another 1 or 2 degrees.
But it's really fucking close.
It is so close.
I wouldn't have thought you'd be able to get it that close. Not you, but a person.
But it's
God.
cool how it stays attached and then
It's just boom!
yeah. Wow, that is cool.
Nice work.
So now I need to figure out, yeah, cruise, it was just a little bit too high, a little bit. Just make another one. Lower the whole pattern on the metal part and keep the one in the plane and go with it. The tuft seems to line up better now than they did previously. There was something that happened here.
I think I just changed the flat position.
Okay. There's a little bit happening back here, but that's kind of normal at that angle. Whatever the angle is. You can see it's working and it's keeping it all lined
That
up.
side, it never even broke loose on that one.
Sweet.
I am very impressed.
This is cool stuff.
The Cirrus guys spent years on this. What were they doing? We got a first shot. What's the hard part here?
Yeah.
To make a long story short, you guys have been hanging on for 50 minutes. I'm not going to drag you through all the details, but right after we finished looking at the tapes, we stood up and walked out to the airplane and figured out that there is a manifold pressure error of about 1 inch, which ties into all the performance testing that we're doing, but we'll get to that on Flight 10.